What happens when two waves arrive at the same place at the same time? They add together, crest on crest or crest on trough, and the result can be brighter, louder, or surprisingly, nothing at all. This is superposition, and it leads to some of the most beautiful and revealing effects in all of physics. This unit builds in four moves: the principle of superposition and interference, the famous double-slit experiment that proved light is a wave, diffraction gratings that split light into precise colors, and stationary waves trapped between two ends. Let's start with what happens when waves combine. The principle of superposition is simple. When two waves meet, the total displacement is just the sum of their individual displacements. If two crests coincide, they reinforce into a bigger wave, called constructive interference. If a crest meets a trough, they cancel, giving destructive interference, and the result can be complete silence or darkness. What decides which you get is the path difference, how much further one wave has traveled than the other. A whole number of wavelengths of difference means the waves arrive in step, giving constructive interference. A difference of a half wavelength, or any odd number of halves, means they arrive out of step and cancel. But none of this works unless the sources are coherent. Young's double-slit experiment is the classic proof that light is a wave. Shine coherent light through two narrow slits and the two beams overlap beyond them, interfering to paint a pattern of bright and dark stripes, called fringes, on a screen. Particles could never do this, only waves interfere. The pattern was the smoking gun. The geometry gives a beautifully simple equation. The fringe spacing equals the wavelength times the distance to the screen, divided by the slit separation. So wider spaced fringes mean a longer wavelength, a more distant screen, or slits closer together. Rearranged, this lets you measure the wavelength of light from nothing but a ruler and the pattern. A diffraction grating is the double slit idea taken to extremes, not two slits but thousands, packed close together. With so many slits combining, the bright fringes become razor-sharp and far apart, which makes measuring angles, and therefore wavelengths, extremely precise. Gratings are the workhorse tool for splitting light into its exact colors. The grating equation is d sine theta equals n lambda, where d is the spacing between adjacent slits, theta the angle to a bright fringe, and n the order, counting outward from the center. Because the bright spots sit at different angles for different colors, a grating spreads white light into a perfect spectrum, like a finer, sharper rainbow. There is one more kind of superposition, a stationary wave. When a wave reflects back on itself, the forward and backward waves superpose to make a pattern that does not travel at all. It just oscillates in place. You see it on a guitar string and hear it in every wind instrument, and it is what makes music have notes. A stationary wave has special points. Nodes are points that never move, where the two waves always cancel. Antinodes are points of maximum swing, where they always reinforce. The distance between adjacent nodes is half a wavelength, and that fixed geometry is exactly why a string of a given length sings at particular frequencies and no others. Here is the whole unit as one poster. When waves overlap, they add by superposition. In step gives constructive interference, out of step gives destructive, and it only works with coherent sources. The double-slit experiment turns this into bright and dark fringes, with wavelength equal to a x over d. A diffraction grating, with thousands of slits, gives sharp spectra from d sine theta equals n lambda. And a stationary wave, from a wave reflecting on itself, has fixed nodes that never move and antinodes of maximum swing, with adjacent nodes half a wavelength apart. And the boundary fence so you do not over-revise. The deeper quantum behavior of light, where it acts like particles, comes in a later unit. The electronics of how signals are detected is separate, and the maths of damped and forced oscillations waits for it too. Here it is superposition, interference, the double slit, gratings, and stationary waves.